This is the fourth video of this tutorial series for the heat transfer analysis on a PCB in Abaqus. So, I believe that our analysis, we will complete our analysis on this video. So, let's start. We have already created the materials and the relevant sections, and we have assigned the sections on the part. This is why the green color is appeared on our geometry. Now let's move forward and create the instance. We have to include our PCB, the part, and part, okay. And let's create the heat transfer step for the heat transfer analysis. Choose the heat transfer. Let's rename it heat transfer. Let's click steady state, okay, and let assist the rest of the parameters. Okay, the field output request has been created for whole model, NT nodal temperature and heat flux vectors, perfect. And as we have already said, in order to include the convection, we have to do it using an interaction tool in Abaqus, which is said surface film condition. Now we have to click the surface that we want. Let's choose only the two large surfaces, the bottom and the top. We could include other external surfaces, but the difference would be small. So click done, and here this is the film coefficient that you have to assign according to this table. So this is the column, the conversion in the Abaqus millimeter inside. So let's put the value of the 0.5, and this is the single temperature. Let's say the ambient temperature of 20 degrees Celsius or 293 Kelvin. Perfect. So this is for the convection. So if we want to continue and assign a load, we have the option of the body heat flux in Abaqus, volumetric heat flux. So what we have to do here is that I've searched it a lot on the web and on the knowledge base of Simulia. Normally the body heat flux units are in watt per cubic meter, but now since we're working in Abaqus in millimeters, what we have to do is to proceed with watt per cubic millimeter, but not to do this conversion. Be careful for that. So what I mean, for example, let's use this tool and measure the volume of the SMT component. This is 4 times 2 times 0.7, it's about 5.6 cubic millimeters. So if we want to assign a boundary condition of a load condition of body heat flux equivalent to, let's say, 1 watt, let's hold the shift key and select all the cells that consists this. It's done. We have to put the value 1 watt divided by 5 cubic millimeters. This is a value of 0.2. Okay, let's do it 0.5. Okay, so I think that we can move forward by creating a job, heat transfer 1 watt. Let's click 2 processors for our analysis and let's submit it. The following steps. Okay, continue. Yes, let's click yes. Submit it. I believe that in a few seconds the analysis will be completed. Let's wait a few seconds. It's running. Nice, completed. Right click results. Let's click the contour to, let's click here NT11 for the temperature, the nodal temperatures, and you can see the contours of the results. You can specify the limits if you want. Click apply, or 4 or 2 or minus. You can also show the locations. Okay guys, this is a complete heat transfer analysis including both convection and conduction modes. The interesting was the partitioning of the PCB, which is a computational efficient way to simulate the traces and include both the copper and the electric FR4 materials. Thank you for watching. Please leave any comments if you have any questions, or hit subscribe if you want to watch more videos.